Well, hello everyone, and welcome to our bonus episode. This is an extension of our conversation of scales from episode 3. If you're like me and you appreciate the arts, but you also enjoy mathematics or are interested by mathematics, this is the right episode for you. We're going to talk about why our scales are the way that they are and the mathematical reasoning behind this. So let's get started. So first, we're going to talk about some desirable traits of scales in general, and I'm going to, throughout this video, explain how our modern Western music system accomplishes, or at least attempts to accomplish, these goals. First, simple enough, we want to have enough pitches for variety. We wouldn't be able to make very interesting melodies with only 2 or 3 notes, would we? We also don't want to have so many notes that we can't tell the difference between successive notes in a scale. So here's our C major scale. We have 7 unique tones. When we go from one note to the next, you can clearly hear the difference between them. There's no question of whether we have jumped a note or stayed at the same note. But even though there's only 7 unique tones, that gives us 7 diatonic chords, and for 5-note melodies, we have 7 to the 5th, or about 17,000 possible 5-note melodies. That's an overwhelming number of possibilities. Not to mention that they could be played with varying types of rhythm, and you may even be able to put some accidentals in there, occasionally put in some notes that are not within the major scale. We want to be able to form intervals within our scales that are pleasing. So with the notes in a C major scale, or any major scale, you can form the octave, the fifth, and the fourth, the perfect versions of them. And this is very pleasing to our ears. We also want to facilitate consistent harmonization with whatever type of scale we build. What do I mean by that? Well, let's look at the first 5 diatonic chords of C major. There are major thirds making up our chords, which are green, and minor thirds, which are blue. We want to make sure that every time we encounter a major third or a minor third, it's going to always be the same. All the blue intervals should be the same. All the green intervals should be the same. Since both of these, this is a D minor, this is an E minor, they're both minor triads, the same kind. Spacing must be the same. Let's talk a little bit more about consistent harmonization. Our system has achieved this through equal spacing of notes. And that means the same distance for every half step. Without equal spacing, making chords and scales is a disaster. And I'm showing it to you by explaining what would happen if we didn't always have the same spacing between notes a half step apart. So most of these half steps are 5 units. Some of them are 6, some of them are 4. And what I've done is I've constructed the C major diatonic triads from these specific spacings, and you already are seeing a problem. Our green intervals are not the same size, and our blue intervals are not always the same size. Furthermore, if we look at the chords that form perfect fifths, which is everything besides a diminished, the fifths aren't even identical to each other. So we have a major problem. And like I said in the previous example, look at D minor and E minor. They're supposed to be the same kind of triad, but yet I see 2 triads with different spacings. It gets even worse when we try to make scales. Turns out that major scales will not sound the same when started in different places, as we had previously said. If we start a scale on C, this is our spacing. If we started on D, we come up with a different spacing. So before I next talk about what constitutes a pleasing interval, it's important to understand the physics of pitch and how we interpret it in our brains. So what is sound? Sound is just a physical wave through a fluid of alternating high and low pressure. So what that means is that when a sound is produced, a pulse of energy is sent through the air, and it causes the air to condense particles in certain areas and have the particles less condensed in other areas. If you are standing still and these peaks of high pressure pass by your ear, they're going to pass by your ear at regular intervals in time. And so pitch is just the frequency of those peaks. How many of those peaks of high air pressure pass your ear every second? If we have a pitch at 440 hertz, that means that 440 high pressure points are passing by your ear every second. When we say that notes are the same distance apart, we're actually talking about the fact that the frequency ratio of both pairs of those notes are the same. So if 2 pairs of notes are the same interval, their frequency ratios will also be the same. which means that we don't hear pitch and differences in pitch by the numerical difference in frequency. We hear it by the ratio of those two frequencies. Now we're going to talk about what happens when we combine multiple pitches together. We combine multiple waveforms, we get the combined waveform in the dotted black line. When the ratio of frequencies is 2 to 1, which is a very simple whole number ratio, we get a pretty consistent combined waveform. But when we don't have a whole number ratio that is simple, like 14 to 5, our combined waveform is a lot messier. Now, it may look like it has some regularity to it, but upon closer examination, we find that if we were to draw a red line in every place where the two waves overlap in peaks, it only occurs in the upper example. It occurs no times in the bottom example. So when we have simple whole number ratios of frequencies, the waves overlap each other often, therefore sounding pleasing to our ear. Let's bring it back to the music theory. We already said the first bullet point up here that we're looking for intervals where the frequency ratio of both pitches is a simple whole number ratio. The octave, the fifth, and the fourth do this very nicely because they form the simplest whole number ratios that you could possibly have. Remember that thing about notes that are an octave apart being the same note? Why do they sound similar if their frequency isn't the same? Well, it's because we have to double the frequency to get to the next octave. This doubling effect creates a sense of similarity. And this is why we can have multiple registers of the same note. This phenomenon is also known as octave equivalence. Thirds are also implicated in these ratios, but these whole number ratios would be less simple. Seconds and sevenths would have even less simple whole number ratios, and therefore would sound the most dissonant or unsettled, unstable, tension-ridden, whatever you want to say. Whereas the more consonant intervals are going to sound very pleasing, calm, relaxed. I'd like to remind you, too, that the most consonant intervals are also contained within the major scale. But now you might be wondering, these pleasing ratios, can we really get them from equally spaced tones? Well, let's find out. Let's look at the mathematics a little bit. First, I'm going to explain what a geometric sequence is really quick. You don't need to know this to understand the rest of it, but I still think it's interesting, the mathematical connection. So geometric sequence is a sequence where to get to the next term, you have to find the previous term, multiply it by a constant value. If we want to write this in a more simple term where we don't need to know all the previous terms to get the current term, we just find the nth term by taking the first term and then multiplying it by our constant value, n minus 1 times. What does this have to do with our pitches? Well, to get to each successive frequency, a half step over, we always have to multiply it by a common value. Because if we're always going up by the same interval, we always need to be multiplying by a constant value. So we do this 12 times to get to the next C. What is the value of A? Well, we know that to get from C to the next C, we could also just multiply by 2. Multiplying by 2 must be the same as multiplying by A 12 times. So A to the 12th is equal to 2. And when we solve for A, we get 2 to the 1 over 12, which is about 1.059. Therefore, we can say that a half step is an interval whereby the ratio of higher to lower frequencies is 1.059. Let's make fourths and fifths with this knowledge. A perfect fifth has 7 half steps. So to get from C to G, we have to multiply this frequency by 2 to the 1/12 7 times. So we're multiplying by 2 to the 7 over 12. For a perfect fourth, it's only 5 half steps. So our multiplier to get from C to F would be 2 to the 5 over 12. How does this stack up to our simple whole number ratios? For the fifth, which is 3 halves or 1.5, we get our 1.498 out of 2 to the 7 over 12. For a perfect fourth, we're also pretty close to our 4 to 3 ideal ratio, but we're not quite there. So our perfect intervals aren't so perfect after all. What are we supposed to do? I'll leave you with a few choices for what we could do to resolve the equal temperament or equal spacing issues. First, don't do anything. I just showed you that the intervals are so close to their ideals that our ears are forgiving enough to be able to pick them out. We could adjust the temperament a little bit to make the intervals closer to ideal. Remember, we'd be changing the spacing so it's not constant. Some major scales would be different than others. In fact, throughout history, the key has been pretty important because equal temperament has not always existed. And because of this unequal temperament, some keys actually would not have the same sound. There's even been attempts to create keyboards that have multiple F sharps, multiple G sharps, for example, that are used in slightly different contexts to overcome this unequal spacing issue. I don't need to tell you, though, that this keyboard does not look very fun to play. Our third option is to just not even use the system, just abandon it entirely. There are other musical systems throughout the world that have really focused on preserving these perfect intervals and not worrying about equal temperament. But of course, without equal temperament, you run into some of the other challenges that I had previously alluded to. So I just want to wrap this up and say that there's this really fascinating intersection between music and mathematics. It goes way deeper than what I've been able to present to you in these past 10 to 12 minutes. I want to remind you of what we just talked about, that our Western music system in modern day allows us to have just the right number of notes, not too many, not too few. We can create complex compositions because we have consistent harmonization and equal temperament. And hey, we also get intervals that are extremely close to the ideal whole number ratios that we're looking for. So at the end of the day, music is an art form, and we have to recognize that nothing can be perfect, but can certainly be worthwhile. So stay tuned for our next regular episode where we're going to be wrapping up scales and chords.